here are the solutions to one of the hypothesis test problems, and has several steps to it, but in the online homework they break it down into pieces. So we're trying to look at a study where we subject people to two different treatments for something. So there's some kind of garlic pill, and there's some placebo pill that I guess looks the same. So the idea is to see which drug makes people feel better. And so you can imagine that what's happened is the subjects are all given the treatments, and then they're asked a question, which treatment do they feel was more effective? So that gives us our P. From the problem, P will be the proportion, I could write, this pen's not working, so proportion, and we can use, again, they're either going to say garlic or placebo, so we can say whichever one we want. So they're going to answer one way or the other, so we should specify one. So let's just say P is the proportion who say garlic is more effective. And so since they have to say one or the other, then what we're trying to find out is if more of them say garlic than don't. And we want to test that in the population, but we're only gathering data from, looks like 111 people. So of the 111 people, I'm getting that by adding these two things together. Of the 111 people, 63 people answered garlic to the question which was more effective, and 45 answered the other one, which was more effective. Of course, they don't know which one is which, right? That's the point of the study. So that means that the proportion of the population who would say garlic, if you could ask everybody who ever had a tick bite, would be our population proportion P. So remember, the variable is the question that we're asking. So we're asking which was more effective, which pill was more effective. So that's the variable, and so we see that here. The variable is whether which one is more effective. So the variable in a statistics problem is really the question that you're asking, and then their answer is the value of that variable. Then the parameter that we're testing is the population proportion for whom they say garlic is more effective than placebo. It actually, you could do the study with either one of these. I don't know why they've, I don't honestly know why they've picked the one that they picked. You do have to decide which one you're talking about because it makes a difference in terms of which you decide to do here. But if you're not sure why they picked this, it really doesn't make any difference which one of these two that you do, as far as I can tell. Anyway, but this is what they're doing, and so that means our hypothesis is we're just testing this against 50% because there's only two answers, and so either it's 50-50, in other words, it's random. That would be that the drug has no effect, the garlic has no effect. If you really thought that half the time people would think the garlic was effective and half the time they thought the other one was effective, that would mean that the drug is not doing anything. So 50-50 is what you would expect if nothing is going on, and it says that it says here, it asks, does this suggest a difference between garlic and placebo? And so that's not saying, does it suggest the garlic is greater than the placebo or the other way around. It just says, is there a difference? So when it talks about a difference rather than one being bigger or smaller, that's when we want to use the not equal to as our alternative. So of these answers, obviously only A, E, and C could possibly be right because we know our null hypothesis has to be inequality, has to be equals. And then the alternative to it is just not equals because all they're asking is there a difference between the two? Okay, so this is our hypotheses that we're testing, and you can see this is going to be a two-tailed test, right? So that means that at the end we're going to have to remember that. This question about sample size, this is something I didn't talk about in class, but basically the sample size has to be big enough. I shouldn't say will, I should say, do we expect at least 15 yes and 15 no. That's sort of the bottom line for having a big enough sample size. That's why a lot of times you'll hear people say that if your sample size is not at least 30, then you won't get statistically significant results. It's actually more than that. It's do you reasonably expect that with this proportion question that there'll be at least 15 people that are yeses in your question and at least 15 people that are no's in your question. So that's kind of the bottom line. So in this case, we're asking 111 people, and it's pretty clear that from our sample that it's close to 50-50. So with 100 and some in the sample, then we certainly expect at least 15 yeses and at least 15 nos to this question. Anyway, so that's what the minimum requirement is for the sample size for these tests. Okay, so then in the problem, they just go right to the test statistic, and you'll remember that that's what I did in class too. I had this test statistic as sort of the next step. I think I did include at least one other step. And the reason it does that is because with the calculator, you could go right to that value. You really don't have to calculate anything else. You could start punching these things into a calculator. But let me just remind you of what we were doing to get that value. The first thing we have to do is calculate our p hat. This is what we're going to use to test our hypotheses. And our p hat is going to be, well, it's got to be consistent with our p. If p is the proportion who say garlic is more effective, then p hat should be the proportion in the sample that say garlic is more effective. And so there were, 63. Sorry, reading the wrong one. So in this problem, it says that of the sample, 63 people said garlic was more effective, and 48 said it wasn't, so that's a total of 111 people. So 63 out of 111 is approximately 0.568. So that's the p hat that we're going to need for our test statistic. We also need to know the standard error. Now, you might be tempted to put this p hat into the standard error formula, but remember, we only do that if the p is unknown. The real standard error formula is this. It's p times 1 minus p over n over the sample size under the square root sign. And so when we were doing these hypothetically in Chapter 7, we really did put a value of p in. It was only when we did confidence intervals, where the value of p is unknown, that we use p hat instead, because it's going to be close. So since we do actually know p in this case, it's the hypothetical value of p. Right? That's the whole idea of hypothesis testing, is that we're building a distribution based on the assumption that the null hypothesis is true, and then we're measuring whether or not that's consistent with the data. And so with hypothesis testing, we do know p. I mean, it is hypothetical, but in our distribution, we know what p is. So I should use 0.5 for this. So I'm not going to try to write, can I squeeze it in there? Probably not. 0.5 times 1 minus 0.5 is also 0.5. And the sample size is 111. So use the real p with in hypothesis testing. And the real p is going to be from the null hypothesis. So now let's see how we're going to get the z-score, our test statistic. We now have enough information to do it. This is where it helps me to actually picture the standard normal distribution, the z-score distribution. Well, actually, let's think about the p hat distribution. This distribution is centered at the true proportion, the p, which is 0.5 because of the null hypothesis. So the distribution that's centered at 0.5, the particular p hat we have is 0.568, so it's out here. So the distribution of the p hat that we've gathered, the 0.568, sits out here on this distribution that's centered at 0.5. So this distribution centered at 0.5, this thing that I've drawn here, this is a hypothetical distribution. This is the distribution if the null hypothesis is true. This is the actual data we collected, and it falls here on that distribution. And so what we're trying to gather is how unusual is that? How unusual is it to have a p hat value of 0.568 relative to this distribution? And so the way we can calculate that is, I can't scroll down. The way to calculate that, the way to calculate the z-score is the z is going to be how far from the mean my value is. So that's the difference. Let me just give myself a line here so I don't run into it. It's the difference between my observation, my observed 0.568, this happened in the data, so that's my observation, and the mean of the distribution, that's the center of the distribution, divided by the standard deviation of this distribution, which is what this calculation is doing. So the standard I didn't actually calculate that. This number, or standard error, turns out to be 0.04, it's like 0.047 with a few more decimal places. So that's the result of this calculation. So my standard error is about 0.047, so that's what goes here. And so if we do that calculation for z-score, that's where this 1.42 is coming from. So as a formula, you'll see in the book, in the boxes in the book, it'll say that when you're doing hypothesis testing, the z-score is the p hat, in other words, the observed proportion, minus what they call p0, that's this number here. That's what the calculator says too. It's the number that goes with the null hypothesis divided by the standard error. And standard error comes from this formula using the value of p0. So that's the formula for z, and so we could just jump right to that. We don't really have to do this and draw a picture and think about it and do that. But I do it this way because I want us to see that it really is the exact same calculation that we've been doing ever since we started drawing bell-shaped curves. So that's the z-score. Finally, the p-value, let me just draw this again. The p-value we're going to get from the z distribution. So 1.42 on the z-score distribution is going to be about there. The p-value is going to be the area that we get from using that z-score. Now, the direction that we shade this in has to do with our alternative hypothesis. Because our HA here is a not equal to, that means that I am not biased towards shading it either higher or lower. I'm going to shade it both ways. And so I'm going to add negative 1.42 here, just add the symmetric value for z, and shade both ways. So this region that's shaded indicates the proportion of the observations that are at least as far away from the middle as this one that we observed. And it's doing it without the bias of saying that we think it's going to be a higher value or think it's going to be a lower value. So this is what we call this a two-tailed test. When our our alternative hypothesis is not equal to, we shade in both directions. We put our z-score down and then draw the symmetric vertical line and shade in both directions. So those are going to be exactly the same area. And so what I normally do is I'll look up one of them in the table or do one of them on the calculator. So if I did normal CDF 1.42 comma 100, for example, that is all of the area from 1.42 and higher. When I do that, I'm going to get about, where'd it go? About 0.76. No, that's not right. Oh, 0.76, sorry. Yeah, so I get about 0.076. So that would be this much area. And then when I double that, I'll get about 0.15. So they've rounded this in a weird way, but the MyLabs Plus seems to be okay with the numbers being rounded in different ways. And Anyway, if I were doing this, I would have gotten 0.15 with my numbers, and I think it would accept that. So notice that the p-value there is twice that, because the normal CDF function or the table is only going to give you the area of one side of this or the other. We know it's a two-tailed test, so we have to double that to get our p-value. So finally, I can't see the choices below. I keep trying to scroll and I can't. But notice that they don't actually give us a significance level, and so when we don't have one, we assume it's 5%. This is 16%, so that's too high. So because this probability is higher than 5%, that means we do not reject the null hypothesis. In other words, we think that this picture is plausible. Now, that doesn't mean that we have confirmed that the hypothesis is true. It just means that we have not gathered enough information to doubt that the null hypothesis is true. And so because we can't doubt that that's true, it means we don't have enough evidence to make this conclusion. So that will be the part C answer here. But we should be saying the p-value is greater than the significance level, so we do not reject the null hypothesis, which means that we don't have enough information to believe the alternative.